We are going to introduce our final project for data mining course. Our topic is wine review analysis. Wine testing is the sensory examination and evaluation of wine, but sometimes it cannot be simply quantified to be numeric features. What if we want to infer the variety of a wine or tell what properties makes a wine taste good or bad, or even tell if the wine should be expensive or has low price? Fortunately, we found such datasets. As we can see, the dataset contains the price points, reviews, and a variety of wine, and some other properties such as designation, region, country, and winery. Except for points and prices, all other data are string, and we decide to focus on 4 problems and try to solve them. The first one is to predict wine type by reviews, and we'll also discover what properties makes a wine good rated or bad rated. Another problem is what most people care about. We want to find how to predict the price of wine. Finally, we'll discover the correlation between between price and wine quality. To classify the wine type by reviews, basically we need 3 steps: pre-processing the dataset, build a model to classify the test data, and analyze the result. Since we got 2 datasets, so we firstly use pandas concat function to concatenate the datasets, and now we need to find if any reviews are null or if there are any duplicates. We simply removing those data, and then we found that there are actually 756 varieties. But if we count the instances for all the varieties, we also notice that most of the varieties do not have enough corresponding instances. So our decision is to extract the first 20 varieties, and for all of them, they have more than thousands instances for us to use as the training data or test data. Since the reviews are stream and constitutes of words, so we cannot work with those texts directly. So we decide to build a bag of words model to throw away all the order information in the words and focus on the occurrence of words in the document. But if we only consider occurrence of words, our issue is that some words they may have large counts and they are not very meaningful in the encoded vectors, such as R is those words we call them stop words. So we decide to calculate the TF-IDF values of the words. It is a product of term frequency and inverse document frequency. Term frequency summarizes the frequency of a word appears within a document. Inverse document frequency indicates the downscale words that appears a lot across documents. So we use TF-IDF vectorizer from scikit's NER library. It could tokenize a word, generate sparse matrices of the TF-IDF, and can even apply the stop words. The paragraph on the top is a description. We can see the tokenized terms with different TF-IDF values after applying a TF-IDF vectorizer on the description. After pre-processing the dataset, we use 2 classifiers. One is the SDG classifier. SDG classifier implements regularized linear models with stochastic gradient descent. Another one is logistic regression for multi-class. Logistic regression provides 4 solvers and 2 multi-class options. By default, the solver is lab linear and the multi-class is OVR. OVR is 1 versus rest. The difference is like OVR has separate classifiers to each classes. In multinomial case, it has the same classifier and it's quite like a perception where you will get a range of score values to each classes. It uses the cross-entropy error. The result is based on the prediction accuracy score. We compare the predicted value with the real value to get the score. At first, we use TF-IDF vectorizer without stop words and default logistic regression, and we get the 0.717. After changing the classifier, we found that the SDG classifier doesn't really help. It even decreases the accuracy score. After we apply the stop words, the result has tiny increase. A possible guess is that the reviews do not contain many stop words. After changing the multi-class option and solver, the classifier runs faster and performs better. Adding a vectorizer based on character analyzer also helps. We combine the two sparse matrices and get a 0.727 score. When adding designation to the description, we get a 0.04 increase on the score because the designation are informational and helps with the TF-IDF matrices.
The second part, we try to build a model to predict the rating using the description in the review. The dataset contains more than 280,000 data, and after describing the dataset, we found the points of all review ranges from 80 to 100, so that we decide to reframe the rating. So if it's from 98 to 100 point, we give the A, and 94 to 97 we give B, so on and so forth. We give 80 to 82 as F. So we totally have 6 rating class, and we totally have 6 rating classes, and the sentiment analysis is used to determine which class a wine belongs to. And we got the result. In the picture, number 5 to 0 correspondingly represents rating A to F. We checked the data information. We found out all entries have description filled out, meaning no missing data, which is good. So we can see here there are total data entries, and each entry has the description. Then we used the NLTK package for analyzing all the description entries. We want to check what words are the most common words that used in the description. This figure shows the result from the top to bottom, with the most frequent to less frequent words. Then we try to find a set of words that can be used as keywords. We pick the most of the adjectives and a few nouns that can express the feelings. And those words showed up in more than 97% of all data entries. Then we use the regression to analyze the relation between these words and the rating. Here is the result with the mean squared error 0.79 and RMSE 0.88. The numbers at the bottom represents the importance of each word correspondingly.
Now I'm going to talk about how did we approach the predicting the price of the wine problem. The first step is data cleaning and transformation. We dropped useless features, removed the duplicate data, and created new features on our own. The next step is modeling. Our first approach for this problem is linear regression. It is ideal for modeling the relationship between the price of the wine and a series of other variables. However, the result is not good. The residual plot of the linear regression model showed a heteroscedasticity, which means that it has failed to capture the characteristic of the relationship between the price and other variables. We then tried other approaches and settled down with decision trees. The evaluation matrix for this problem, we used a mean squared error and R2 score. With the use of decision tree, our performance improved a lot, and we tried various modifications to improve the performance of the model. The first improvement we did is adding categorical features to the feature set. In the early iterations, we only used the numerical features. Adding categorical features such as country, province, region 1, region 2 turned out to be very useful. The next one is feature engineering. Feature engineering is a very crucial part of data mining. Only using raw features to train the model is not good enough. In our dataset, take feature variety for example. It is not just a normal text label. We can extract information about the wine from it. Variety Zinfandel represents a full-bodied red wine, while Variety Riesling indicates the lighter-bodied white wine. Based on the variety feature, we can get grape type, and wine style. The next technique we used is bagging. The decision tree models are very sensitive to the training dataset. If the dataset changes, the resulting decision tree can be very different. Bagging is a technique that can be used to reduce the variance for decision trees. With bagging, we combine the predictions from multiple decision trees so that we don't have to worry too much about individual tree overfitting the training dataset. Tuning the bagging temperature parameter is our way to adjust the bagging. The last one technique we used is boosting. Like bagging, boosting is also an ensemble technique. Instead of aggregates the results of each model, models in boosting determine what features the next model will focus on. The library we used called cat boost implemented gradient boosting and it improved the performance a lot. Here are the results of all models. The columns are mean squared error and R2 score, and the rows are different models. From the top to bottom, linear regression model, the basic decision tree model, the decision tree with categorical features. The next one add feature engineering to it, and the last one we add bagging to it. You can see there's a big performance gap between the linear regression and the basic decision tree model. The mean squared error dropped from 1100 to below 1000. And the tree decision with categorical feature performed better than the one with only numeric features. The mean squared error decreased from almost 1000 to over 700. This is understandable. The model can predict the price of the wine more precisely when it includes all related information. Feature engineering also helped the performance of the model, which means that we extracted some useful information. It helped the mean squared error dropping almost 100. The last row showed the effect of the bagging parameter. We can see that the performance improved slightly. For this, predicting the price of the wine problem, the decision tree model with categorical features, feature engineering, bagging, and the gradient boosting performed the best and extracted the most useful features. However, since we only have very limited amount of data, we still run the risk of overfitting. If there are additional datasets or libraries that can provide more comprehensive information, we can combine our current datasets with them to fully exploit all features. This time, we only tried linear regression and decision trees, and there are plenty of room for improvement. If we have more computation resource and data in the future, we can try to use other methods, such as artificial neural network, to approach this problem.
Hi, welcome to our final project. This project is about wine reviews. This is Yitong. I'm in charge of part 4 of this presentation. It is named Discover Correlation Between Price and Wine Quality. So let's get started. For the whole procedure, we have several steps to take. The first is data cleaning. As we have 2 data sets and some missing values, so this stage is very necessary. Second, we need to do data transforming and visualization. With the help of visualization, we can get an intuitive understanding of the relation between the 2 variables. Next, we apply linear regression to gain quantitative insights of these 2 variables. We also need to do correlation coefficient calculation. Apart from this, we can also check out the individual characteristics of price and points, so we can know how these 2 variables behave by themselves. Last but not least, we can do estimation of the regression model. And last, we can also do further exploration for the distribution of the wine quality by price. About our analysis results, we can see from the slides that the Pearson correlation for the two variables is around 0.4, and the coefficient of the regression equation is around 1. So this brings us to the final conclusion that the correlation between price and wine quality really exists, but it's not naively linear. From our final distribution plots, we can also see high score wines can be found across different price spectrums. If we have time and energy, we can do some future work. Like in our previous analysis, we only deal with data about involving price and wine quality, which is points only. But we can also interact with other variables like country, region, and winery. So we can calculate correlation, coefficient, conditioning on these column variables that we are interested in. The other thing we can do is to do net text analysis on given descriptions. We can use word cloud for help.